Welcome back, everybody, to the second part of the lecture. So I'll start with a question on the Zoom chat, then I'll finish with the 9 remaining slides that I have, and then we move on to the next parts. All right, so go ahead, Wenji.
So in terms of physical storage of H files, I suppose we split them into HDFS blocks. If so, when we merge 2 small H files into one, do we simply fetch the corresponding HDFS blocks of the small H files, then create a new HDFS block for the new single H file, and then delete the old HDFS blocks?
Yes, this is pretty much what happens. This is pretty much what happens because indeed, what I explained here with the H files and so on is from the perspective of outside HDFS, right? Hbase is a client of HDFS, and it's just using HDFS like anybody else uses HDFS. So I didn't speak at all about the HDFS blocks and the name node and the data node and so on, because this is just a lower detail of the physical storage. But nevertheless, it's a very good question to ask. And I actually will have more slides about the interaction with the HDFS. Actually, I can even show you, because maybe I can use the opportunity of your question for that. Because indeed, Hbase runs on HDFS. It means that it's the same machine that has the region server responsible for the regions, and that also is a data node and has the blocks. So you're absolutely correct that the H files that you want to compact, the blocks are likely to be here on the same machine, especially if they were recently written down, right? Because you know that HDFS has a life, right? And if you wait a bit, then some of the blocks might at some point end up somewhere else, right? Because, sorry, you know that there is some rebalancing, sorry. There is some rebalancing in HDFS. And if there are too many blocks on one data node, then they will be just, you know, pushed to other nodes in order to compensate. So if it's very recent that the H file was written, then the blocks are on the same machine, and then you're effectively reading the blocks locally and then compacting them and reading and writing them down again, and you're deleting the old blocks. But if you wait, you will have some of the blocks that are not available on the same machine, and here you need to go through the network, right? You cannot just short circuit by directly reading. You have to fetch them over the network using the HDFS protocols, right? But what happens, and this is the magic, is that the next time that a compaction is going to occur, we will read all of these blocks, most of them here, some of them from other data nodes, recompact, and that brings back everything on the same machine again, because these are the newly written blocks, and we saw that the client, it's always the same machine as the client when you write the first replica of the block. Of course, there's a replica somewhere else too, right? So you see that what's a very nicely engineered feature of HDFS and Hbase is that every compaction, every flush brings back the locality. It makes sure that there is a first replica of each blocks on the same machine. And this is why it's so fast, because these are all local reads here most of the time. It's very rare that you actually go there. Now, it's very nice to think at that level. What's important is that you are aware of the modularity. Let me give you an analogy. You will understand what I mean. When you go to the restaurant or to the Polymensa, let's say you're going to go to the Polymensa in a few minutes, you go there, you enter, you go and grab what you want to eat, right? You queue, you take a menu, you grab I don't know, maybe a drink, one of their absolutely tasty desserts. Sometimes they have really great dessert in the Mensa, and then you go to the cashier desk, you pay, and you go and eat, right? But you know that for the Mensa to actually work, there are people working. There are people who are doing the cooking, who are preparing the dishes, who are putting who are making the desserts, baking the desserts, and putting them on the shelves and so on, right? But when you go to the Mensa, maybe you don't have that in mind. You just focus on the appropriate level of abstraction, which is grabbing what you want to eat, paying, and going to the dining part, right? But if you want, you can also go to the Mensa and maybe try today as an exercise with the awareness that everything you grab corresponds to a physical level of implementation of all the food that you're taking. And in a way, what I'm doing here is pretty much that. It's like going to the Mensa with the awareness of the cooking and everything that happens behind the scenes in there, right? And in computer science, we like to have these levels of abstractions because all the levels of abstraction is what makes us build an ecosystem that is robust, right? Okay, I hope that makes sense, the analogy that I've just done. Did I answer your question?
Yes.
Yeah, question answer. And we have another one. Yeah.
Another one is that, so when you say a region server is in charge of a region, does it mean it's in charge of compacting the H files of the region?
Yeah, exactly. That's what it means. It's in charge of flushing, it's in charge of compacting, and in charge of also serving the fetching the key values and serving them to the client. Yeah. All right. Okay, you're following. That's absolutely great. And what I really like is that you ask exactly the right questions, because all the questions you ask basically give me the transition to go to the next part. So it leads to a very natural flow in the lecture. So that's really great. Okay, now I have a few slides. I'm going to show you something crazy. It's an optional part, but just to show you how we can even take them to the next level, because you may think, okay, thousands of machines is already a lot of data, right? Petabyte is already a lot of data, but some people just don't have enough of that. They want even larger scales. So it turns out that there's technologies that have been developed later that take it to the next level. And one is called Spanner, is developed at Google. There's also the F1 database that was based on that. We had a guest lecture a few years ago by an engineer of the team. So maybe you can find it if you're interested. It's probably recorded somewhere in the ETH multimedia services. But anyway, it's very similar to Hbase, but there's a few differences. The first one is that the row ID can be multiple columns, not just one column. Another difference is that here, what we call region, they call tablets, but the tablets can be made of several non-contiguous parts, right? So this is a bit of difference. So they relaxed a little bit the model. But now comes the absolutely fantastic part. You thought, okay, that's going to be a billion, but no, it's actually a trillion. We can have trillions of rows in there. We scale even more. We scale beyond what we've done so far. Trillions, I think they even mentioned quadrillions in the papers of rows. And then you might think, okay, one data center is not enough, right? And indeed, one data center is not enough, because now they have this HMaster, whatever they call it, region server and so on. But now they have a universe master that itself is centralizing all of these local clusters. So you see, this is how you go to trillions and quadrillions. So you add a level 0, 1, 2, so an additional level, the universe master. That starts sounding a bit like a science fiction movie, right? Okay, we can have hundreds of data centers. So now we're even scaling the data centers, like maybe this is Frankfurt, this is Munich, this is New York, this is San Francisco, this is Zurich. I mean, yeah, all of these data centers. And we have now not just thousands, but since we have so many data centers, we're talking about millions of machines, right? So you see that just the scale that we are looking at is just amazing. It's a point where you just start counting the zeros, basically, when you do that. All right, but this is what I wanted to show you, just to show you that what we did with Hbase is only one cluster, but there are even ways to take it beyond cluster and have clusters of clusters, to have quadrillions of records. All right, I'm stopping here for this part. I'll move on to the next slide. So I'll see you in just a few seconds to go with the next part.